my topic given for my seminar is design of structures for seismic loads. And to start with the topic, so we're going to see what is a seismic load and what are the conditions which we require for selecting the site, and with an example problem. So what is a seismic load? The assumed lateral load an earthquake might cause, which acts upon a structural system in any horizontal direction. So seismic load is nothing but the horizontal load which comes to the building when the movement of tectonic plates are seen under the earth's surface. So what are the steps involved in seismic design? The first step is planning stage. So at the planning stage, what are the steps we require for selecting the site? So the plan of the structure should be in such a way so that it's symmetrical in both horizontal and vertical axis. So that during earthquake, when the load is acted upon the building, the resistance will be in both equally distributed in horizontal and vertical direction. So avoiding open grounds. So if the story is raised to more than 10 to 15 meters, the foundation has to be strong. It's based upon the type of soil which you find in the site, and providing of openings. The openings which we give, such as doors and windows, should be a minimum of 0.6 meter away from the column edges, so that during the earthquake load, the column gets more stiffness. When the openings are avoided. And going to the next slide, soil test. Soil test has to be initially performed before doing the construction of earthquake building. Because based upon the soil, the foundation will vary. Because the soil is clay, pile foundation is mostly preferred. And following of IS code, IS 1853 is mostly is seen for design of earthquake resistant structures. And select of good materials. The concrete which we're going to use should be of graded more than M35 or M40, and the type of steel which we're going to use should be of yield strength of minimum of IS 415 Newton per mm square. And provision of beams, lintel beams and plinth beam should be given at each floor level, so that the stiffness of the building can be enhanced. And this diagram represents different earthquake seismic zones which are seen in India, and upon which Chennai comes upon zone 3. Going to the next slide. So steps to design for seismic loads. So the code of practice, as I said before, used is IS 1893 part 1, and we're going to see an example of a 4-story building, how the seismic load is designed for a 4-story building. And moving to the next slide. So this is the elevation of the structure which we're going to design, and the structure is about 40 meter in height and 10 meter in width, and it is divided into 4 bays, each of K1, K2, K3 and K4. And this is the plan of the building, where the columns are divided into transverse and longitudinal columns. Alright. So moving to the next slide. Building data required. So these are the data which are required for construction of for the design of the building. So type of structure, as I said, the type of structure is 4-story building, and the seismic zone which we are going to consider is zone 4, and the number of stories is 4, G plus 3 that is, and the height for each floor height is 3.5 meter from floor to floor. And the infill wall is nothing but the partition wall which we use in the building, which is about 250 mm thick. And the imposed load which we're going to consider is 3.5 kN per meter square. And the size of column, we're going to assume it to be 250 by 450 mm, and the size of beam to be 250 by 400 in longitudinal direction and 250 by 350 in transverse direction. And the depth of slab which we're going to take is 100 mm thick. And specific weight of RCC, as you all know, is 25 kN per meter cube, and the specific weight of the infill is 20 kN per meter cube. And the type of soil which we're going to consider is rock soil. It's not a clay soil, it's a rock soil. Moving to the next slide. Calculation. The first step is calculation of lump masses. Lump masses are nothing but the dead masses which we find in the building, which is nothing but the partition walls and the partition walls and the covering walls which we find at the above the beams and the lintels. So the calculation of lump mass is done by at 2 stages. One is at the roof level, and another one at the different floor levels. So at the roof level, the imposed load is not considered, and at the roof level, the lump mass is calculated as mass of the infill plus mass of the column plus mass of the beam in both longitudinal and transverse direction plus mass of the slab plus imposed load of that floor is if permissible. So as I said, for the roof level it is calculated to be 37.08 ton, and for different floor levels it is calculated to be 64.45 ton. And all these loads are added up to give the seismic weight of the building. So the entire seismic weight of the building is to be M1, the addition of all these masses, so which comes to 230 ton. So as I said, the seismic weight of each floor is equal to full dead load plus imposed load, and the dead load is not considered at the floor level. The step 2 is determination of fundamental natural period, which is nothing but the vibration time of the building. So it is given represented by TA. The formula is 0.075 H per 0.75. So it is nothing but the height of the building, by which it is found to be 0.54. Moving to the next slide. We have determination of design base shear. The base shear is nothing but the shear which comes at the base of the building, after which it is being transmitted to the entire height of the building. So the base shear, the shear at the base is being calculated using the formula AH into W, and AH is given by Z by 2 into I by R into SI by G. And SI by G is nothing but the inverse of the vibration time, so which is calculated to be 1.842. And substituting in the formula, we get AH as 0.0443, upon which the base shear is calculated to be 99.33. And after the calculation of base shear, the last step is vertical distribution of base shear. As I said, the shear which comes at the base of the building is being transferred to the entire height of the building, and it is given by QI, which is the design lateral forces at each floor level. And it is given by QI is equal to the base shear into seismic weight of each floor into height of each floor divided by summation of seismic weight into the height of each floor. And by substituting the values which we got earlier in the formula, we are getting the design base shear to be 4.306 kilonewton. So similarly, for all other each floor it is being calculated, and it is being represented in the following diagram. As you can see, the base shear is comparatively large at the bottom when comparing to the at the top end of the building, where at the top end of the building it is found to be 39.646, and at the bottom it is found to be 99.933. And the loading diagram is represented in the following manner, where at the top one it is found to be 39.646, and it is comparatively getting low as we go lower to the building. Thank you.